Good day, students. I am Ajiboye Adebayo. You are welcome to another chemistry session. Today's topic is on isomerism. Introduction. Two organic compounds or more can have the same composition but have different reactivities. This is as a result of different arrangements of the atoms in the structure of the compounds. Objective. At the end of this lesson, the student will be able to 1. Define isomerism, 2. Describe the different types of isomerism, 3. Write different isomers of an organic compound, 4. Determine the chiral center of a compound. Now, what is isomerism? Isomerism is a phenomenon in which more than one compound have the same chemical formula but different chemical structures. Chemical compounds that have the identical chemical formula but differ in properties and the arrangement of atoms in the molecules are called isomers. Therefore, the compounds that exhibit isomerism are known as isomers. The word isomer is derived from the Greek word isos and meros, which means equal parts. This term was coined by the Swedish chemist Jacob Berzelius in the year 1830. Now, types of isomerism. There are two primary types of isomerism which can be further categorized into different subtypes. These primary types are structural isomerism and stereoisomerism. Now, the classification of different types of isomer is illustrated as below in a chart. Now, so we look at the chart. Now, isomerism divided into structural and stereo. Then under structural isomerism, we have 6 of them. We have 1, chain, we have positional, we have functional, we have metamerism, tautomerism, and ring chain structural isomerism. While that of stereoisomerism could be classified into 2. We have the geometric and the optical isomerism. In geometry, isomers differ in their spatial arrangement about a double bond, while the optical isomers differ in the arrangement of atoms in 3D space, which creates a mirror image to each other. Characteristics of isomer. Now, number 1 is that they have the same molecular formula but different structural formula. 2 isomers can have different boiling point. 3 isomers have the same atomic weight and same number of atoms. 4 they show similar properties only when they contain same functional group. Now, we take it one after the other. Structural isomerism. Now, in structural isomerism, the atoms are arranged in a completely different order. Structural isomerism is commonly referred to as constitutional isomerism. The functional groups and the atoms in the molecule of these isomers are linked in different ways. Different structural isomers are assigned different IUPAC names since they may or may not contain the same functional group. The different types of structural isomerism are as follows. So we first of all look at chain isomerism. Chain isomers are made up of 2 or more carbon or other compounds with the same molecular formula but different atomic arrangement or branches. These isomers arise because of the possibility of branching in carbon chains. For example, there are 2 isomers of butane, that is C4H10. In one of them, the carbon atom lies in a straight chain, whereas in the other, the chain is branched. Now, chain isomerism is also known as skeletal isomerism. Now, another characteristics of chain isomerism is that the components of these isomers display differently branched structures. Commonly, chain isomers different in the branching of carbon. An example of chain isomerism can also be observed in pentane, that is C5H12, as we have below. Now, one of the isomer of butane, of pentane, could be the normal pentane. We also have 2-methylbutane, and we also have 2,2-dimethylpropane. Thank you. I will see you for the next class. Now, welcome back. Now, we move on to the next one, which is position isomerism. Position isomerism occurs when a functional group is in a different position on the same carbon chain. The positions of the functional groups or substituent atoms are different in position isomers. Typically, this isomerism involves the attachment of the functional groups to different carbon atoms in the carbon chain. An example of this type of isomerism can be observed in the compounds having the formula C3H7Cl, that is chloropropane. So we can have it as 1 chloropropane or 2 chloropropane. Here, the position of the chlorine determines the name of the isomer. Now, another example is found in butanol, which is C4H9OH. C4H9OH. So, in butanol, we can have it as we can call it butan-1-ol, which is generally known as butanol, or another isomers of butanol that we can have is butan-2-ol. This is when the OH is at carbon number 2. Then we can also have another isomer that we can have is 2-methylpropanol. That's 2-methylpropanol. And also we can also have it in 2-methylpropan-2-ol. Now all these are isomers of butanol. Now we move on to functional isomerism. Functional isomerism. Molecules are classified according to their functional groups, or groups of atoms or bonds with unique chemical and physical quality. Now, let's take a look at some functional groups where R and R prime are side groups that consist of carbon, hydrogen, and or other elements. For example, if a functional group is CHO, which is a carbonyl, that means CHO, which is a carbonyl, is attached to a molecule, then this molecule is classified as an aldehyde. But if a functional group of OH, that is hydroxy, is attached to a molecule, then the molecule is classified as an alcohol. Then functional group isomers. Then functional group isomers have the same molecular formula but different functional groups on the chain. For example, ethyl alcohol and dimethyl ether have the same chemical formula but different functional groups. So we can also have an example of that. An example of functional isomerism can be observed in that compound which we've mentioned earlier, ethanol and C2H5, that is our ethanol. So we can have it as ethanol, which is C2H5, or methoxymethane, which is our dimethyl ether. That is CH3OCH3. CH3OCH3. So that is our functional group isomerism. Now we move on to metamerism. Now this is a type of isomerism arising due to the presence of different alkyl chain on each side of the functional group. It is a rare type of isomerism and is generally limited to molecules that contain a divalent atom such as sulfur or oxygen surrounded by alkyl groups. Example is found in C4H10O, which is represented as ethoxyethane or diethyl ether. Diethyl ether could also be C2H5 or C2H5. I repeat, C2H5OC2H5, that is diethyl ether. And we can also have it as methoxypropane, or methylpropyl ether, that's CH3OC3H7. Now we move on to tautomerism. Tautomerism is the existence of two or more chemical compounds that are capable of fissile interconversion. In many cases, merely exchanging a hydrogen atom between two other atoms, to either of which it forms a covalent bond. Unlike other classes of isomers, tautomeric compounds exist in mobile equilibrium with each other, so that attempts to prepare separate substances usually result in the formation of a mixture that shows all the chemical and physical properties to be expected on the basis of the structure of the components. The most common type of tautomerism is that involving carbonyl or keto compound and unsaturated hydroxyl compound or enols. So the structural change is the shift of a hydrogen atom between atoms of carbon and oxygen with the rearrangement of bonds. So I will see you again. Now, welcome back. Now, let's quickly look at the ring chain isomerism. In ring chain isomerism, one of the isomers has an open chain structure, whereas the other has a ring structure. They generally contain a different number of pi bonds. Compounds having the same molecular formula but possessing open chain and cyclic structure are called the ring chain isomers, and the phenomenon is called the ring chain isomerism. For example, propene and cyclopropane are ring chain isomers. Now, we go to the second aspect, which is stereoisomerism. This type of isomerism arises in compounds having the same chemical formula but different orientations of the atoms belonging to the molecule in three-dimensional space. The compounds that exhibit stereoisomerism are often referred to as stereoisomers. This phenomenon can be further categorized into two subtypes. One, we have the geometric isomerism. Now, geometric isomerism is popularly known as C-strand isomerism. These isomers have different spatial arrangement of atoms in three-dimensional space. Geometric isomerism, also called C-strand isomer, are a type of isomer resulting from a double bond or a ring structure. The double bond or ring in the structure means that not all bonds are free to rotate, giving rise to a geometric isomer whose shape cannot interconvert. Now, the simplest example of geometric isomer are cis-2-butene and trans-2-butene. In each molecule, the double bond is between carbon 2 and 3. In cis-2-butene, the methyl group attached to carbon 2 and 3 are on the same side of the rigid double bond. In trans-2-butene, the methyl group are on opposite side of the double bond. Optical isomerism. Now, optical isomerism. These optical isomers are also known as enantiomers. Enantiomers differ from each other in their optical activities. Dextroenantiomers rotate the plane of polarized light to the right, whereas levoenantiomers rotate it to the left. Optical isomerism occurs when substances have the same molecular formula and structural formula, but one cannot be superimposed on the other. In other words, they are mirror images of each other. They are referred to as optical isomers or enantiomers. Molecules like these are said to be chiral. Optical isomers can occur when there is an asymmetric carbon atom. An asymmetric carbon atom is one which is bonded to 4 different groups. It forms a chiral center of the molecule. Now, in a chiral center, the 4 groups can be sometimes hideously complex, or something comfortably simple like a hydrogen atom or a chlorine atom. Now remember that for a chiral center, there must be 4 groups and they must all be different. So we can see the difference between chiral and achiral. Now we can see that the central atom for a chiral center is asymmetric because the substituents attached are different. But in an achiral, the central atom is symmetrical, that is, 2 substituents are the same. An example can be found with butanol, that is, butanol, the carbon atom to which hydroxyl group is attached is an asymmetric carbon atom, and so it has different groups that is attached to them, and so butanol is optically active. Now another example of an optically active compound is the lactic acid. The lactic acid is CH3CHOHCOOH. That's the lactic acid. So that is that's the formula of the lactic acid. So they are optically active. So optical isomers can rotate the plane of a polarized light. The negative, that is the minus enantiomers, rotate the plane anticlockwise, that is to the left, which is also referred to as the levo rotatory, symbolized as L, while the plus enantiomer rotate the plane clockwise, that is to the right, which is also referred to as dextro-rotated. D and L is the exact same with plus and minus. The DL system is also known as Fischer-Rosanov convention. It's mainly used for naming alpha amino acids and sugars. It compares the relative configuration of molecules to enantiomers of glyceraldehyde. This convention is still in commonly used today. A very good example of this is found in the allelburic glucose D, which is sold in most supermarkets. So the D in the name shows that the glucose rotates a plane polarized light to the right. Now, a mixture containing equal concentration of plus and minus enantiomer is not optically active. That is, it will not rotate the plane of polarization. It is called a racemic or a racemate. Thank you for listening. Hope to see you again.